This second video in the Smartphones in the Astronomy Classroom series will focus on the general benefits of simulations and the specific characteristics of smartphone simulations. Astronomy simulations are useful tools for interactive engagement. Students using them actively construct understanding from their experiences, creating links between new knowledge and their existing knowledge. We are especially interested in helping students build models of astrophysical systems and see connections between disparate things by forming strong mental representations of astronomical phenomena. The screen capture shown here illustrates a simple simulation focusing upon the connections between the celestial equatorial and horizon coordinate systems. Noting the location of a celestial pole in the sky and its relation to the observer's latitude is a necessity for understanding star motions and trails. However, with the demise of Java and more recently Flash, the astronomy community has taken a step backwards in regards to simulation availability. More good simulations in general are vitally needed by the community. A few HTML5 simulations specifically targeted at smartphones and appropriate for in-class usage are available at astro.unl.edu/smartphone. Here we verbalize the design characteristics of these simulations and how they vary from desktop simulations. Keep in mind that these tools will be used on devices with small screen real estate, and all datasets used will need to be downloaded on each use. The planned initial usage will predominantly occur in the classroom where limited time is available. Thus, the simulation should target a more narrowly focused parameter space than would be implemented in a simulation designed for desktop usage outside of the classroom. We endeavor to provide a logical design to the graphical user interface so that no sophisticated manipulation should be needed. We want our simulations to be conceptually intuitive. Students should be able to discover all functionality through experimentation and prior experience. Complex interfaces are not appropriate for quick classroom use. We also endeavor to ramp up the complexity that students encounter. This may consist of various aspects of a simulation being shown in isolation first, before being shown with other components, or simply dividing up the capabilities into a number of smaller simulations. A screen capture of the orbit's view of the planetary position simulator is shown. Although this simulation has very sophisticated elements, the first component is modest and could easily be used by itself. Let me mention a corresponding set of characteristics from a computer science perspective. These simulations make use of adaptive layout, resizing and reorganizing their components based upon the resolution of the particular device. They will adapt to either landscape or portrait orientation, although one is likely to be preferable to the user on their particular device. The simulations also make use of scalable vector graphics that will retain their sharpness on higher resolution devices like desktop monitors, unlike simulations made with the JavaScript canvas. We also make use of JavaScript pointer events to obtain similar behaviors on different devices, such as selection by smartphone touch and desktop mouse. Our simulations also contain embedded questions and activity prompts to guide a student's exploration. The questions are numbered to allow easy assignment by faculty. When a simulation is divided into pieces, the questions are also divided accordingly. Some questions require that the simulation be placed in a certain state, a combination of hiding the answer, setting certain slider and checkbox values, and disabling unneeded components. The questions endeavor to span a range of difficulty. There are straightforward questions provided for students early in the learning process of the topic, promoting experimentation and interpretation of the simulation, while at the other extreme are questions based upon challenging skills requiring iteration that may be left for usage outside the classroom, or at least not on the first day of using the simulation. Here you can see the embedded questions for the labeled shadow diagram, the first component of the Eclipse Explorer. Let me give you a short tour of the capabilities of the Star Trails Explorer. Note that this simulation package has two linked simulators, each of which can be used individually and then in combination. We start out in Sky View, which allows you to set an observer's latitude, show the sky looking in any cardinal direction, and then animate the motions of the stars. From Lincoln, Nebraska's 41 degrees, you can observe the stars circling the pole looking north, the lazy circles looking south, as the south celestial pole is below the horizon, and star trails making a 49-degree angle with the horizon in the east and west. Switching to horizon diagram, we now see the star trails from a global perspective, appearing to circle the axis of Earth's rotation connecting the celestial poles. Note that 3 special stars are emphasized: Star A, which passes through the north point of the horizon, Star B, which passes through the zenith point, and Star C, which rises at the east point of the horizon. The eponymous both views facilitates students building a mental model relating the 2 representations. Let me illustrate question Q3C. Note that this question has a setup button which places the simulation in a certain state. Setup specifies a certain latitude, hides the latitude slider, and then asks students to specify the latitude from the visuals displayed. Note that these are HTML5 simulations, so they should work on everything. A lot of what I have showed you so far have been screen captures taken on a desktop computer screen for convenience. But let me use a document camera to convince you the simulations do work well on all mobile devices. Here is the Star Trails simulation on an iPhone X. I can capture the screen directly on the device, but you wouldn't be able to see me pushing any buttons. Note that it is quite responsive, and there are a lot of stars with spherical trig calculations going on for them, and then mapping to the device coordinates. Let me move to an Amazon Fire tablet, which is in the Android family. This is the smallest Fire tablet at 7 inches, so this model does go on sale for $35 on occasion. Although it is a no-frills device, it is perfectly adequate for using these simulations. Let me finish with a Chromebook, which I have placed under the document camera. You can see that the simulation works well once I have narrowed the window width to a value similar to a smartphone in portrait mode. Note that I can now manipulate the simulation using either touch or mouse on a Chromebook. So these simulations can be used effectively on a variety of inexpensive devices.